Simulation is wrong. Yes? Everybody has a simulation. Okay, you are, of course. You have everything. Okay, very good, very good. Okay, please open your simulation. So everything is so slowly here. Very, very slowly. And then today we need also understand theory of flow simulation. What is important by flow simulation? It's only two things important maybe. Yes, in other way, two new things. That's important by flow simulation, and we need to understand today. So, okay. Okay, and yes, what we did. Okay, we try to calculate this task. Yes, our ball connection. We have press stress. We have fluid pressure. The question is, breaks our part or not after 1 million loads. So, okay, and this question we will answer this today. But first, I need to open. I need to open file. Yeah. Okay, not so good. I don't have file. I didn't have used this stick last week. Okay, it needs a lot of time. Okay, and what we need to do today? Today we will try to answer, to understand that program control is not the best solution. Yes, program decide what program doing. Yes, but we will see today if we have knowledge, theoretic knowledge, we can do our simulation quickly. So, okay, I don't know what's happened with ANSYS. Where is ANSYS? Hello. Okay, we need to wait. And the main thing about simulation at the end we solve system of linear equations. Yes. So, and every software has same story, same two types of methods. So sometimes you can choose many types of direct method, many times iterative method, but it's very important to understand the difference between direct and iterative. Yes, you have to do it manual. Deriv is the most quickly method what we have since 300 years. Gauss found solution. Yes, if all elements not zero, then it's the quickest method. So, and what is good with this method, we try to get zero elements under main diagonal. Yes. So look, we make 1.5 diagonal. Yes, in these places have to be 1, and under this line have to be 0. So look how we do it. Very easy. First we divide it with 8, for example. Yes, and it's important to understand that we will see now in simulation how it works in ANSYS. So, okay, we divide with 8, then we have 1, yes, and then we can make plus, minus, and then we can get 0 elements under 1, yes. And then same story, we divide with this point, then we have 1 in main diagonal, and then we can create 0 under diagonal, yes. And at the end we have this system, and we can say x, x1, x2, x3. So this is a very good method, yes, n cubic multiplication. So you need to solve this system. So iterative method is different, yes. It's also with iteration. We say, for example, solution is 0, 0, 0, yes. So then we check our system and we see it's not 0, 0, 0, yes. We have this error. And then we make next step, so with new results. And then we are doing many iterations. Why we are doing it? At the end, for example, after 23 iterations, I found solution. Yes? So iterative method means I need many iterations. The problem is I don't know how many iterations I need. Yes? And every iteration costs n quadrat multiplication. So, and as a next problem, maybe I cannot find solution. So, for example, with direct method, I will find always solution. With iterative method, it's possible that I will not find solution. So, okay, and why do people use both methods? Very simple. If I have, for example, 100,000 equations, or for example here 3 equations, yes, I need 27 multiplications here. And here I need 9 multiplied with 30, I don't know, 200 and 300 multiplications, yes? So it's much more slowly for small systems here. But if I have 1 million equations, then here I need 10 in the power of 18 multiplications, and here maybe I need, I don't know, 1000 multiplied with 10 in the power of 12, yes? Then this method is 10,000 times quicker. So, what you have to know, normally direct method, I will say 100,000 knots to 300,000 knots, and here for million knots is quicker. So, and we will see today. Yes, in ANSYS we can make every theory what we know, and we need to check it. Is it really so or not? So, okay. What we did before? What we did last time? I opened my file, and I show you again. We will start again simulation from this last week. So, main knowledge we need to know. We need to define material properties, stress strain diagram, yes. We need to define these all things like RS6 no, ledge deflection on, nonlinear properties, yes. This is main things, and then we need to create good meshing, yes. It's better hexa mesh, with sweep method or multi-zone method. So, and we did it. So, we did it. For sweep method, yes, we need special geometry, like one inlet, one outlet in one direction. So, and our main target to divide everything, yes, to get this possibility. Super. You have result. It's better to show maybe megapascal. Oh, now it's better. Not so many people. Very good. Yes. Okay. Oh, I was by Siemens last week. They are doing also software, and we bought one license to try. So, and then it was, I think, 10 people who they want to show what this software can. 2 people who want to learn, yes, and 6 people from Siemens showed everybody full day how it works. It was interesting. Okay, good. And you didn't do something wrong. Okay. So okay, I do again. I mean, it's not so many people is better for simulation. Okay, S command, simulation, very important thing. So, okay, I repeat again what we did, and then you can understand again something more. Okay. Today we will finish our mechanical simulation, then we are doing flow simulation. So, we are starting with flow simulation. So, but, yes, main target we need.
I opened the module.
So now it's so slowly, I don't know what's happened. Okay, and then we will check how we can use our theoretic knowledge to be quickly, and second question, how we can say breaks our pattern or not. So this is the main questions for today. Okay, I don't know what's happened. Come, please open me so slowly. Save. Okay, please open your old simulation. Your simulation, task 3. So, okay, I hope it works. Okay, again. And we need to calculate first this part. Okay, this example, press stress of the bolt and fluid pressure. So, and we will calculate maximum stress. Okay, I have to repeat it. What's happened? Something is bad. Doesn't work. Come on, ANSYS. Oh no. Okay, I have a problem.
It's not going.
Hello, come on. Ah, it's very slowly here. So, and okay, please open your simulation. Okay. Okay, we will try to do it. Yes, we will try. Since we have same state. Okay, not too bad.
Oh, yeah.
Sure.
Right, pause.
But something is wrong. Slowly here. Okay, now I opened something. It's good. Okay. What's happened? Not connecting to a local license. Hey, come on. Everything closed. Oh, come on. French schließen. Oh, yes. Okay, now again. And then I save in Felix and we can use it today. And then we will see what's happened. Okay, how we can use our theoretic knowledge and how we can say breaks our pattern node. Okay, and now break and use. One. Okay, I'm opening model. I hope this is geometry with a good mesh. Or if it's not so, then we can use normal meshing, standard meshing. Important is to show what we can do, how we can do it quickly, our simulation. Okay, this story with hexa mesh is only to save time, yes, to save time and to get a more exactly solution for short time. Okay, now we will see what's happened. Come on. Oh, it's so slow. Okay. So, started mechanical and has somebody mentioned or has somebody model? You have? No. Okay, you did it. And you? Did you solve? Now solve. Here solution, right mouse button, and then solve. Everybody, okay, you did it. And you did it also, very good. Okay, I hope it's open, and then for everybody who didn't do it, I will say it very fast. Yeah, okay. This file for Felix. Okay. Now I try to open it. It's also the okay, then I don't know, say maybe this is file and then I lower the exit. Model is my I save also no. Oh no, it works, look. Something works and not quite. And what's happened? Oh, it works. That's good. Okay, then I saved now file the links. Where is geometry? Okay. Okay, it's not. I don't have now good meshing. Yes. And we will try to do it with this basic task. Yes. So For good mark, you need to do it, yes, with good meshing in your practice work. And we are doing now with normal meshing. I save this file then in Excel, in the Felix, and then we can start together with this example. So we can create. Okay. Okay, the best solution, we divided everything, yes, but we need time for this, yes, and then we will get good results. So this is the main task, and now that we have same state, I do now this simulation with tetra mesh, yes, and then I save this meshing in Felix, and we will see. And we will speak about how we can say breaks our part or not, yes? So this is the main subject, and how we can use theoretic knowledge in the simulation. So, okay, maybe we need to do it a little bit finer. It looks more beautiful. So like in lectures, yes, in lectures you can also find solution with tetra meshing. Okay, what I did here some elements, yes, size. Okay, what we did everything 2 and 5 millimeter and 0.5. Okay, so we can say everybody's 2.5 millimeter size, and only radius is 0.5. We need final solution here. It will not so beautiful solution like with hexamesh, but it will be yes, solution. Okay, it's now we need to change units. Yes, don't forget to change units to millimeter. It's number 3 by units, and then we say 2.5. And every software like SolidWorks works only with tetra mesh. It's easy. Yes, you don't need some knowledge. Yes, you can make fine meshing and then it works automatically. So, but you don't have so good results, and it needs a lot of time, this calculation. So, for example, now I have 50,000 knots, and it looks not so good. Look, yes, it's two big elements. I need maybe this growth rate. I have to change. Maybe it's I don't know, 80% next element, and we can change it and say we need not so many elements. Yes. Okay. Okay. Here we don't see. We need to say maybe mechanical nonlinear. Yes, and then we can change this grow rate. For example, 1.2, and then we will see how it looks. It has to be better. Okay, now it looks much more better, yes, okay. Here is fine, with 1.2 growth rate. Normally I use always 1.2, it means 20% next element bigger as last element. So 20% is very good, yes, then it looks fine. And you see it's not so fine like hexamesh, yes, for example, here in radius, yes, I have only 3 elements. By hexamesh we can do here 10 elements, yes, and it looks really fine. So by tetramesh I have 3 elements, and it costs 100,000, yes, and we did meshing with 50,000, much more beautiful and fine. So, and now with tetramesh it's not so easy to do it. Okay, and maybe 90 is too much, and then we need a lot of time to calculate it, and maybe I do this meshing not so fine. Okay, it's not so good, but what can we do? Okay, we can say maybe 0.7. Then I save this file in Felix, and we can calculate it together. So, for example, now it looks not so good meshing, yes, but okay, 70,000. Okay, I don't know how we can create about 50. Maybe it's here 3 millimeter. So I want to do about 50. So I think it's possible only about 50. Okay. 35, maybe bigger element, yes. Maybe 3.5, I don't know, and phase size 0.6. Okay, this is not good solution what we are doing, yes? So, okay, 55,000. We need to refine this place. This place is very important, yes? But I cannot do it, yes? I can do it finer, but other mesh will also fine. Look, if I change it and say 0.4, then I have, look how many elements. Only 4 elements in radius, and I have 90,000, yes? It's, for example, if you do it now in a hexa mesh, yes, you say not 4 but 8 elements, then you will see maybe 1,000 nodes more. And here, if I do this radius fine, then I have 40,000 nodes more, yes? It's everything fine. And this is a problem of SolidWorks and other cheap simple simulation softwares. So, okay, the main target is to understand breaks our part or not. Okay, I stay by this meshing. It's okay. 55,000. It looks not fine, but it's okay. So, okay, and maybe these 2 elements looks not so too big. Yes. Okay, we need to calculate it, and here we have contact. Maybe we need to say this place finer. 3 millimeter or 2 millimeter maybe. Okay, and these bodies have to be fine, and these contact bodies, yes. And then we can do it maybe a little bit finer. So, and then I save it in Felix. But everybody who has model, please use your model, yes. So, okay, you see problem, yes. I did here fine, and then everything is fine, and then I have again 70,000 elements. So it's really not so good working with tetra mesh. Maybe a little bit bigger. Okay, it's so like this, 60,000. I hope it works with student version. We will try it. Okay, now I start simulation. Then I save this file for everybody. So what is important to know? We need nonlinear material properties, of course. Yes. So we did it last lecture. So I repeat again what we have to do. So we need to say nonlinear material properties. Yes. So it will be good to repeat how I can define it. I'm going to engineering data, and then I say I have new material, duplicate. Then I say my material is 1.4435 steel. So, yes, and then I need to define material properties. Yes, how I can do it? I will find in internet these points, and then with Excel file I can recalculate it in ANSYS in bilinear, for example, kinematic hardening. Yes, it's stress strain diagram in megapascal. So I did it with Excel, this recalculation. And I say my yield strength is, my tensile strength is 318.8, and my tangent is how much? 618.5. So, okay, then I defined nonlinear line. We see this line stress strain diagram here. It's not linear. And then I can close it, and I can go back to the model. Okay, and then we will say, we will define all important things. Yes, all important things is all these 4 things. What we need to say to the program for the real calculation. I don't know what is it. Okay. And then we will check the result with a good and with a bad mesh. So, okay. And if it works, then everybody gets these files. Okay, 2-step simulation. So now we have to wait. Okay. So it's everything what we need for the good simulation. So we need to define material properties like bilinear or multilinear diagram. The best way is true stress, true strain. Yes, second recalculation with ANSYS, or we can find an internet measurement, for example, database, and recalculate it in true stress, true strain. Then we need to define every material is 1.4435. So here we can change it. Nonlinear effect, yes. It means program use now nonlinear lines. Material properties, then we have to define ledge deflection on. It means program calculated always new geometry calculate. Yes, geometry is changed during our calculation. Yes, if I pull one beam, then this beam will be less in diameter. So my geometry is changed always. I say on, then I have to say insert command R6 no, then we have correct results. Okay, every point costs our calculation time, but it's better as calculate for wrong simulation. Yes. So okay, then what we didn't say, nonlinear effect, yes. Analyze ledge deflection, R6 no. Material properties, yes. Everything is okay. And then what we need to calculate contacts, of course. Yes, we have 3 contacts. First contact between our tubes is frictional, 0.1 normally coefficient. Then we have contact between bolt, yes, and tube is also frictional contact, 0.1. Then we have second, 4 contacts we have, yes. Then we have again frictional contact, 0.1, and then we have our mother-father contact. Here is bonded, that means together, then it's okay. So, okay, then it's important to define symmetry. We have 2 symmetry element of two symmetry faces, and we need to say here insert symmetry, and we need to define symmetry first. One side is symmetry region. This all faces is symmetry faces, and important to say normal direction. In my situation is epsilon here, and other side is also symmetry region. So, and apply, and this is in x direction, so x. Okay, symmetry we defined, and then we need to define boundary conditions. We have 2 steps, yes, it means we say number of steps 2, yes. Okay, auto time stepping is better to define, not program control. Program control is always bad, so we will see it today. It's better to say if we know what is means, then it's better to say concrete. For example, I want that first step will be 10. It means not 1 second, but 0.1 second first step. Then I say minimum is 5 steps, for example, maximum step 0.2 second. Yes, and minimal what's possible is not important. We can say a million. It means if something wrong, the program goes down, 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 down until 1 divide this million. Yes, times 2. So okay, but if something bad, then we will see that it's bad. So okay, so we did it 2 steps, and now we need to define boundary conditions. First, we have only preload. Preload with 16 kilonewton. It means I can say this phase insert. We have special boundary condition bolt retention. Yes, so we see it optical. What it means, and then we say first step is only bolt retention. 16 kilonewton. It means half model is 8 kilonewton. Preload 8,000 newton. And first step we have, it means 0 Newton, 1 second means 8,000 Newton, yes, by simulation. And second step we say log, it means we have this preload, and then log, it means we are doing nothing more with this preload. So it stay how it is, yes. It means, for example, if I say 8,000 again, the program try to do always 8,000. Yes, for example, if I say now temperature is higher, it means my geometry is bigger, and then it means my preload is more. Then we see it by simulation. Yes, now log means 8,000 and nothing more. So, okay. And then what we need to say again, preload, and then comes pressure. Yes, of course, pressure. Pressure is 5 megapascal, and question is, breaks our part after million times this pressure load, 0 max, or not. So we have pressure here. Here is flow with pressure, 5 megapascal. We say pressure here, and it's only step 2. It means first step we have preload, second step we have pressure. So 5 megapascal. Okay, we did it, and now I start simulation. We will see. Is it wrong? Something wrong? No, of course, something wrong. Now our geometry fly away. Yes, we need to fix something. So, and we say, okay, here this part, for example, is. We can say, for example, okay, it's better to use this remote displacement. Then we can say concrete what is possible, what is not possible. For example, here I say Z is 0. Yes, it's not allowed to go to the Z direction. So, for example, radial direction, x, y, everything, no problem, but Z is 0. So, okay, and then I can do the simulation. And what we are watching always, it's interesting by working, yes, we are watching force convergence. This is our main criterion. It's like absolute same like by iterative method, this convergence. It shows us, for example, 0, 0, 0, then I calculate my system, yes, left part of my system, 0, 0, 0, then I see with 0, 0, 0, I have here 5, for example, yes, first equation. And right in the equation I see 10, it means my error 5. So, and this iteration shows me my error during calculation. Yes. So, for example, now error is so much, and target is red line is actual error, and criteria is my error. What is good? Yes. What is not so big? So, for example, 4 Newton is. It means I calculate now 300,000 equations. Yes. If I make sum for all equations, it's not so big. So, and you see. Every time we calculate system of linear equations. So first we program try to calculate 0.1 second. 0.1 seconds means 8,000 Newton. It means 800 Newton. Try to calculate program. So, and you see iteration number 3. Every iteration system of linear equations. So, and program tried to calculate first this situation. This one system of nonlinear equation. To calculate system of nonlinear equation, we need to calculate many system of linear equation. And we see we are near. The problem will be if we grow up our error. It means time step was too big, for example. Yes. So then program cannot calculate it. So, and then we see what's happened if our error less than blue line. Then we found solution. Yes, for 0.1. Okay, it looks very good. I save this file, and then everybody can use it in Felix. I make stop. And then we start the simulation again. It looks really same like mesh. You can understand it. Yes, you understand it that what we have with ANSYS, we have this possibility to be quickly. Yes, but if tomorrow somebody tell us, I found algorithms. This algorithms works. I don't know. System we calculate for n multiplication. Yes, it means we don't need ANSYS anymore. So it means we can use every cheap software for free soft, make 100 million nodes, start, and then after 10 seconds we get the result. Yes, this is the same solution. Tetra Mesh is same solution. SolidWorks same solution. Same strategy. One possibility in ANSYS for this expensive software to be quickly. So ANSYS give us possibility to be quickly if we know why. So, okay, and we see now other points of ANSYS, what we can change. Okay, I save this file. Okay, archive. It's called task 3. For example, 19. Save. Okay, or without result, then its file is not so big without result, and then you can go to the Felix and you can start the simulations and we have same state. But for your practical work, you need better to do it with hexamesh. Yes. So, okay, Felix. Okay, now I can start my simulation. Yes, I saved file. Yes, then I can start again simulation. It needs some time, and we will see results. So. Okay, now, I start, I'll go to the Felix first. Später nachfragen. So, Felix through. And then everybody can start simulation together. We can start together the simulation. And we will see quality of results, of course. And we need to answer the question how it works. How can I say breaks our part or not? This is the main problem. Okay, Felix through. Okay. Oh, one second. Amazing. Maybe I cannot go to, yes, it was problem last. Yes, it was problem last week, yes, that I cannot save something in Felix. Maybe this Internet Explorer problem, I think, or can I? Firefox. Matcat Prime. What you are using also? MATLAB.
You already received me.
Matcat. What the program is? Felix have to. So the simulation. Okay, I start the simulation again. I show a really interesting thing in new versions. It's some new thing and very, very good. It was dream to have this. Look what we have in new version. Now in new version you can see results during solution. It's a very cool function. So for example, before, if my simulation needs 2 hours, yes, I'm interested to see how it looks results now, yes? Then I can maybe show the scaled results to understand did I mistake or not. And now it's very good, you can see solutions during calculation. Here solution information, insert, and you can say stress plot tracker. And then you can say switch to automatic mode. It means program show you all calculated solutions during calculations. Very, very cool to see during calculations what's happened. But we need, of course, results. So now we don't have results, yes. After first green line, we can look, we can see, or after second, we can see results. So again, we calculate 0.1 second. And do you see, it's also interesting to see, yes, that sometimes we have also, I think last week, this situation in real simulation. Look, this very good example now for study. Look what's happened. I can start again the simulation. So what's happened? We see now what program exactly calculated how. So look now. Okay, now the program starts to calculate. We see first, second iteration. Okay, first iteration. It was some time, needs some time, then second iteration. Okay, now it's not so quickly, yes? I wanted to say that second was much more quickly as number 3, but no, it's not so. Sometimes you can see that, for example, second iteration needs now 5 minutes maybe, yes? So it works, for example, every every half minutes comes one iteration, and then you have pause 5 minutes, for example. Yes, it means that program try to do this iterative process and cannot find solution. You're waiting, and maybe program tell you no solution. Yes.